Okay, so now we are at the last what you need to know list topic, which is know some of the lipid reactions. The first lipid reaction that we're going to cover is hydrogenation. And this is something that we covered back in week 2 when it is one of the organic reactions that we talked about. If you guys remember, hydrogenation is the addition of hydrogen molecules across a double bond. So in terms of lipids, it will turn an unsaturated fatty acid into a more saturated fatty acid. Or sometimes what it will do, and this is something new, it will turn a cis fatty acid, and most of the fatty acids that are unsaturated are cis, and I'll show you what that means, into a trans fatty acid. Bottom line, the net result of hydrogenation is that the melting point of the lipid goes up. It becomes more solid at room temperature. So what you're doing is you are taking a liquid oil, adding hydrogen molecules to it, and turning it into a solid fat. Okay, that's what hydrogenation will do. Even the flipping of the double bond from cis to trans makes it more solid, makes it have a higher melting point also. So let me show you on a molecular level what is going on. So I'm going to draw out expanded carbons, not overly expanded. I'm going to kind of condense it so that I have enough space. So these are 7 CH2s. So instead of writing CH2, 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 I've got 7 CH2s. And this is carbon 1, and then I have 7 more. That's 8. So this is carbon 9 and carbon 10. Okay? And then let's say I have 7 more CH2s, and then carbon 18. So this fatty acid here, this is oleic acid. So what if I wanted to hydrogenate oleic acid? Let's say this is a fatty acid that is found in olive oil. It's also found in corn oil and sunflower oil. So it's found in lots of oils, all right? So what I want to do, but it's definitely found a lot in olive oil. If I have only one double bond, so I just need one molecule of hydrogen, one H2. That's it. If I had 2 double bonds, I'd have to have 2 H2s. If I had 3 double bonds, I'd have to have 3 H2s. This is something we did back when we were talking about hydrogenating alkenes. All right, so with a platinum catalyst or a nickel catalyst, and some heat and pressure, just like we did with hydrogenation back in week 2, what's going to happen? Well, think of these H's. I'm going to do it in red so that you see the difference here. This is H and another H. It's a diatomic molecule, all right? So now the double bond is going to break. Double bond is going to break, and we're going to add, I don't want to read, I guess I can read, I don't want to redraw it. I won't redraw it. I'm just going to just go directly back to this. So as if I'm redrawing it, but I'm not going to. I'm going to break this double bond, all right? And what's going to happen? You see those 2 red H's? One H is going to come here, and one H is going to come here. Do we have oleic acid anymore? No. What is this now? It's 18 carbons, saturated, no double bonds. This is now stearic acid. And if you look at the literature, stearic acid has a melting point of 80 degrees Celsius, so it's pretty high melting point, so it's definitely solid at room temperature. Oleic acid has a melting point of around, and these are all approximations, around 16 degrees Celsius. So If room temperature is about 25 degrees Celsius, this is liquid at room temperature. Oleic acid is liquid at room temperature. Stearic acid is solid at room temperature. How did we turn oleic acid into stearic acid? We added a molecule of hydrogen. Okay, and that is what hydrogenation is. Now, what do I mean when I say you can switch a cis to a trans? Okay, let me show you what happens. So we have a double bond. Okay, now I'm just going to take this and elaborate. Then the double bond breaks. And the two hydrogens come on, just like we did earlier. But then, and this is where it gets interesting, one from here and one from here go away, and you get a double bond again. But look what happened now. Instead of having the two hydrogens on the same side over here, when they're on the same side, it's called cis. You now have a double bond. It's still unsaturated, but now they're on opposite sides, and this is called trans. When they first started noticing trans fats, I remember I was a grad student, and they were like, what are these things? And they thought, oh no, they're going to like cause cancer, and they were just very worried about trans fat. And trans fat, all it is that it behaves like saturated fat in your body. So they always tell you eat more unsaturated. Well, this looks like it's unsaturated because it's got a double bond, but it behaves more like a saturated fat. All right. So there's cis fats, there's saturated fats, and there's trans fats. Trans fats, how do you get them? You get them from hydrogenation, where the hydrogens add on and then they get removed and everything flips. So when they're on opposite sides of the double bond, that's trans, same side is cis. So the original fatty acid, oleic acid, two hydrogens on the same side of the double bond. You then added two hydrogens, you turned it into stearic acid, no double bonds. And then the two hydrogens went away, and now it's flipped, and now you have a trans, and this one has an actual name. This new fatty acid, this one's called eleidic acid. So eleidic acid is exactly like oleic acid, but what's the difference between oleic and eleidic? Oleic is cis, eleidic is trans. All right. Why is this important? Well, you may have heard about trans fats, and they label this as trans fat free because they realize that trans fats are not the good fats. They are not healthy fats like the monounsaturated and polyunsaturated are, even though they're unsaturated, but your body treats them as if they're saturated. They're the ones that tend to increase your serum cholesterol, clog up your arteries, and stuff like that. Okay? All right, so that's hydrogenation. The next one is hydrolysis. And you may remember this from our organic reactions. Hydrolysis meant we're going to break something with water and an enzyme, all right, or some type of catalyst. So if we have a triglyceride, and I'm just going to do some generic triglyceride here. All right, so this is my generic triglyceride. And why am I saying generic? I'm just going to rest of the molecule. So this is rest of the molecule 1, rest of the molecule 2, rest of the molecule 3. So it doesn't really matter what the fatty acids are because hydrolysis doesn't affect the fatty acids. All right. So this is my hypothetical triglyceride. All right. And now I'm going to add 3 molecules of water. Remember, water is HOH. And then I'm going to use the enzyme lipase. In fact, this is exactly how your lipids are digested. you have the enzyme lipase in your small intestine, and then with the water, it will break these ester bonds, all right? So we're going to do HOH, and what are we going to end up with? We're going to end up with the original glycerol and then 3 free fatty acids, okay? So we're going to do a complete hydrolysis. In your body, you only do a partial hydrolysis in the small intestine, and usually you will break it down to turn it into a monoglyceride and 2 fatty acids. Anyway, but for now, we want to do a full hydrolysis. We want to break all 3 ester bonds. So you break the ester bonds, you end up with an H coming here, OH coming here. See what we did? Maybe I should remember. We have H, OH, H, OH. Broke the ester bonds. You guys see that? So we have at the end a glycerol. Remember, glycerol was 3 carbons, 3 alcohol groups, and then you're going to have 3 free fatty acids. Fatty acid 1, fatty acid 2, and fatty acid 3. So hydrolysis of lipids means you have water and the enzyme lipase, and you end up with glycerol plus 3 FA, 3 fatty acids. Okay? That's what complete hydrolysis is. Partial hydrolysis, you'll just be maybe breaking 1 of the ester bonds or 2 of the ester bonds. But when you're hydrolyzing a lipid completely, you break all 3 ester bonds. It's like the opposite of esterification. Okay? And then the last reaction is saponification. I think I'll do one more video just on saponification, and I want to show you how soaps work so that next time you're washing your hand with soap, you remember chemistry. Okay? All right.